All right, this is Frank O'Brien, and I'm going to try and give you an overview of insulation diagrams. Um, so let's dive in. Um, the objective today is to provide electrical protection for a home use thermometer. There's a process that I'm going to try and introduce you to and show you the flow. The first thing we need to do is categorize our touch surfaces. Applied parts are accessible surfaces. For applied parts, we're going to classify them, call it B, B, F, C, F. For the accessible parts, we're going to risk assess those. It's clause 4.6, sometimes called the MOOP, operator patient type protection. We'll show you how you do that. And then once we have that information, we're going to put together an insulation diagram. That'll specify insulation parameters. And then you've got your test plan. Those insulation parameters will need to be verified after you've built the prototype. So let's see if we can do this. Touch surfaces. Formally, we use the standard test finger to figure out what's touchable. It's rather obvious in most cases, so we don't always need the finger, but that's the formal process there. Home use, the 1-11, there is a small child test finger in addition to the regular finger. We're going to have touch surfaces, the necessary contact for a clinical function. That's going to be your applied part. So for a thermometer, it's what we put in our mouth. And the accessible parts would be everything else. When we draw insulation diagrams, on the right there you can see the applied part is usually a block arrow, and then the rest of the equipment, accessible parts, is typically a box. Applied parts get classified. There's a B, body contact. There's BF, body floating. And then there's cardiac floating, the heart in a box. And then any of those could be with defib proof, the two paddles there. 8.3 is where we find classification constraints. So 8.3a talks about direct cardiac applications. And if we had that, we'd have to be CF. B talks about constraints in that there's patient connections that are intended to deliver electrical energy or an electrophysiological signal to or from the patient, in which case you have to be F-type, BF, or CF. Now, for a thermometer, we are getting from the patient an electrophysiological signal, the temperature. C is if A and B didn't apply, then we could be anything we want, including type B. With particulars and collaterals, you could see additional requirements superposing the C catch-all. In fact, 1-11 for home care talks about applied parts having to be F-type, BF, or CF. So in summary, if we had to classify the applied part of our thermometer, we'd see that 8.3b does in fact mandate BF or CF, and the home use would mandate BF or CF. We don't need CF. It's not a direct cardiac application, so we're not going to worry about that. We don't need defib proof. Nobody's going to be needing. It would be a rather remote probability that somebody would need heart fibrillation treatment while defib while getting temperature. Patient environment. That's the formal word for the environment in which the patient can touch the medical equipment, as well as the operator may be touching the equipment and being able to touch the patient. So it's a slightly bigger area than just a patient's reach. Within that environment, we assume all medical electrical equipment resides. But there is a special case where we allow operator-only contact. The operator might have setup or service type functions. Consider the battery compartment with a door. The door didn't need a tool to open. And we assume that while the patient's not around, an operator might touch battery voltages, low voltage, and be able to swap those out, put the cover back in place if the patient's around. Similarly with data connectors, signal input parts, signal output parts, when they're in place, there's no live parts. The pins are low voltage, but when they're being unplugged or set up, we may have access to this low voltage for operators. As long as there's no patient, it's fine. So if we look at safe limits, things that wouldn't need to be kept away from patient, applied parts where they're in contact with the patient for the clinical function. We see with B and BF, you have your 100, 500, your 100 micro normal condition, and 500 microamps single fault condition. Same with BF, body floating. CF has the lower 10 and 50 microamps. Now with F-type, we actually put the mains on the applied part and check for leakage back through the equipment, presumably earth. And with BF, we'd allow 5,000 micro or 5 milli. With CF, we'd limit that to 50 micro, similar to single fault. When we go over these values, we need to separate that from patients and operators with protection. Accessible parts, same 100, 500, because within the patient environment, we don't have just operator contact, we have patient-operator contact. So similar to type B applied parts. But for operator-only contact, we would allow this 42.4 volts peak and 60 volts DC. That would have to be true in normal and single fault. So effectively, that's your two means from higher voltages. That would need to be limited to 240 VA or 20 joules. So if we're going to exceed those safe limits, and often we would, if we're going to do anything useful with our electrical energy, there's two golden rules. Rule 1, 851, from all touch surfaces to parts that exceed those limits, let's have two means of operator or patient protection, MOOP or MOPP, for the working voltage. And the second golden rule only applies if we have an F-type applied part. It's 8521. From that F-type applied part to all other equipment parts, we need at least one means for patient protection, one MOPP for the mains voltage. All right, so let's take a look at golden rule number 1. We've got the hazard, which is a part that exceeds safe limits, and we've got somebody that we don't want to have touch access. So the risk control would be two MOPP or MOOPs, and we'd need to verify the insulation parameters, check the leakage current for the safe limit. But if we were able to do that, we'd have a acceptably small risk that there'd be harm. So there'd effectively be no harm. Golden rule number 2, the hazard is actually mains on the patient, if you will. And the hazard would be completed if somehow that F part had a path to other equipment parts that would be earthed. So we will risk control that with one means of protection, patient protection. That's to back up presumably a single fault that's already occurred, allowing mains on the patient. So there is two means to prevent such disasters, and our equipment provides the one backup. Again, there's insulation parameters and leakage current that would be verified, and we would have no harm. All right, so accessible parts. Clause 4.6 in the standard opened up the idea with edition 3.0 that accessible parts don't always need to be exactly as safe as Type B applied parts. In fact, we might want to allow less, which is what we call operator protection in terms of electrical insulation. So if we parse out the text that's in that clause, it says accessible parts that can come in contact with the patient. Now these would be direct patient contact. So the cabling on an applied part could brush against patients. So the operator, in effect, is bringing it in contact with the patient. The patient might bring himself into contact themselves. They may touch a handle or a footstep, or even within a gantry, touch the inner bore of the gantry, etc., etc. With a bed, you wouldn't have to necessarily be conscious. Certainly, an active patient can reach out and touch all sorts of surfaces. So, if it's the direct contact, we're looking at Clause 4.6 to give us some guidance on what to require. There's also that situation within a patient environment where the operator could touch a surface and then the patient. That's outside of 4.6. That's mitigated by, in all cases, the medical leakage current limits. There's no direct contact, so operator temperature surface limits are also appropriate. So we're talking about direct patient contact. And then it says the risk management process shall include an assessment of whether such parts shall need to be subject to the requirements for applied parts. So in effect, this part, if we decide, will be as safe as Type B applied part, or maybe more. So if the answer is no, we've got no applied part requirements. We're not going to apply them. And with yes, we are. There's a second decision. If we're going to do the applied part requirements, except that marking symbol, which we saw, then does the assessment identify a need for the requirements for a Type BF or CF? So no would be the Type B, which is presumed to be the default. Or with our assessment, would we want to do the F type? Now we might want to do that if the parts are very close to the patient and close to the applied part, and the applied part's F type, and you could see logically that probably that part might want to be F type as well, but not necessarily. So how do we make this decision with risk? Risk should be probability and severity. The standard's unclear, but there is rationale. If I think about experience with manufacturers, a lot of devices today are based on old legacy devices, and so the design doesn't change much. Recall that we didn't really use the third edition until about 2010. It's only 10 years ago. Well, that's a long time. And yet we still see a lot of patient protection in medical devices where 4.6 might not require that. So it is sort of an area where manufacturers do have difficulty. So what I've tried to do here is set up a severity probability risk evaluation matrix for Clause 4.6. So one of the severity, and again based on the guidance in Annex A, Clause 4.6, one of the severity criteria would be patient health, I'm suggesting. Are they able to respond to negative stimulus? So if you're, for example, unconscious, anesthetized, or incapacitated, we should probably be more careful about what we apply to that patient. If the patient can respond to negative stimulus, then maybe if they touch something, they can untouch it just as easily. Remember, these aren't surfaces associated with the necessary contact for the clinical function. The other criteria that we might think about with severity is the type of applied part. F-type applied parts effectively lower risk um, because they're floating and they kind of control a return path, so they can kind of mitigate against combined leakage current. They can, in the extreme situation, prevent, if mains was on the patient becoming earthed by our equipment. So again, injury-related criteria. So we've got both of those on the horizontal axis there. And on the vertical axis, we've got the duration of contact. Is it going to be similar to the contact that we'd have with an applied part, this surface, or is it going to be less? So what we'll see there is generally when the patient's unhealthy, there's a lot of amber colored boxes there. And in fact, the F-type similar duration applied part would presumably suggest that the pseudo applied part requirements, the accessible part that should be subject to the applied part requirements, would be F-type. And when we subject an accessible part to applied part requirements, we use the term pseudo applied part. It's a useful term that I use, but it's not a term you'll find in the standard. The last row down there on the bottom is the accessible part cannot contact the patient. So I've included that row because it gives us the full patient environment picture. But this is more the situation we talked about where the operator could bridge, but the patient can't contact it directly. So I've indicated, of course, across the board, even the unhealthy patients, that we're not worried about that situation. We could do the operator protection, the not applied part requirements. On the healthy side, we see a lot of green. On the other hand, with the F-type applied part and a similar duration to the applied part, we'd suggest as well that the accessible part have the type B requirements, pseudo type B. So it should make some sense, and it provides a bit more of a black and white approach to clause 4.6. If we think about our thermometer, there's the general enclosure, the white enclosure, if you will, and this is a type B F applied part. And now we've got the accessible parts in close proximity. Real no clear border between the applied part and the accessible part. It's not like it's a lead set with an electrode or a pad. It's in your mouth, and depending on the size of your mouth, who knows where the applied part is. So it seems to me that it's similar duration, at least some of the enclosure. And because we have an F-type applied part, really the enclosure should be this F-type as well. So the general parts of the enclosure should be the pseudo F-type as well. But there was the little button in the display. And I think if we think about an active patient, that they could touch that and just as easily untouch it. And if we think about, and so even for an F-type applied part, this matrix suggests that we could probably go operator protection for that. And on the unhealthy patient side, we're really looking at a patient that's not going to touch that. They're incapacitated, if you will. So, so we could probably go operator there as well. So we've got our applied part, we've got our accessible part, we've done our risk assessment. It's always the same two golden rules on the applied part, that's clear. We've got accessible parts where we've chosen to do some pseudo applied part stuff. That's going to be the 1 and 2 because, again, the second one would apply for an F-type. And then we've got our area, the operator displaying and button, where we're going to do operator protection, so that first rule would be applied with the MOOP insulation strength. So here's a diagram, if you will. The gray tip there with the block arrow, if you will, that's your applied part. That's the metal tip. And there's a thermal sensor in there. Maybe it's an NTC. And it's potted. That blue is an insulating compound, and it's thermally conductive, we would presume, for a good design. And so our insulation A is through the potting material, and B is the general enclosure. And whenever I have an F-type applied part, I like to use a red dotted line. It kind of helps me visualize where the F-type insulation is. And so whenever I see an insulation barrier across that, I'm reminded to always apply that second golden rule. I'd always look for at least my one means for patient, means for mains. So B will need that single MOPP for 240. By the way, it's a battery operated product, Y240. So that's specified in a working voltage clause in 8.5. 2 means for 5 volts is our working voltage. And so we would need both of those. We'd look to both of those up, and independently creepage, clearance, dielectrics. For MOOP and MOPP, we'd always pick the greater. C is our operator area. So here are the 2 MOOP. Operator protection for 5 volts is what we'd specify. All right, and then on the table there, we'd normally fill in some creepage, clearance, and dielectric strength, but where are we going to get those values? So what is creepage, clearance, and dielectric strength? DTI is distance through insulation. So I wanted to illustrate those first. Creepage is that irregular surface there on the left where we've got a distance to mitigate tracking, arc-type tracking along its surface. And so that distance should be appropriate for the dust and moisture and the tracking resistance of our base material. And that's creepage. And that's why it's a risk control. Air clearance is the shortest path through air, and that could be weakened by repetitive peaks as well as transients on our mains. Lightning switchgear out on our transmission comes into our buildings. For example, 240 volt mains, we presume that it's common to have 2500 volt peaks. And it could be higher, but that would hopefully be more rare. But the common general peak we'd want to worry about is the 2500. For example, solid insulations illustrated on the right there. That looks like a transformer with a center flange bobbin. That center flange separates our 2 windings. Dielectric strength is going to tell us the strength of that solid insulation to provide separation. And in some cases, an effective center flange single material would have a thickness requirement if it was providing supplemental or reinforced, and the voltage was more than 71 volts peak, such as 240 RMS. We'd need 0.4 millimeters, for example. And that's in 882. There's another concept where we do use potting materials, or on a board it might be conformal coating. This kind of illustrates a cross-section of a board with 2 foils where we want to separate those circuits, and we've used a coating, a conformal coating, if you will. And that's fine as long as there's no air there. So we call that situation a cemented joint if we have good bonding, no air, no bubbles, no delamination, no cracks. And so 893, 2 and 3 talk about situations where we do a 30-day thermal cycling test, one or the other, depending on if we have plastic to plastic or just plastic to conductive parts. Here to be 8933, 2 plastics. So the thermal cycling, every 3 days it goes hot and cold. So there's 10 hot and cold cycles. The joint has an opportunity to kind of expand and contract and maybe demonstrate that it's not going to delaminate, crack, and things. There wasn't a lot of bubbles when it was prepped. So after the 30 days, we kind of cut it, look for its possible physical damage. We do 160% dielectric test before that. And if it passes, there's no creepage and clearance requirements. Presumably that could be quite small based on the solid insulation of the coating. So creepage and clearance, which are requirements for air, wouldn't be applicable. And recall in our thermometer, we're imagining the tip is potted. So where do we find creepage clearance and dielectric strength? So patient protection has in 891 a table 12, and in 883 this a table 6 for dielectrics. With operator protection, 891 has a table 16 for creepage, and the clearance in a main circuit is tables 13 and 14, and table 15 is for secondary circuit clearance. And dielectric strength is in that same table 6, so there's some columns for patient as well as different columns for operator. Generally, operator parameters are going to be less than patient values, less but appropriate, certainly safe. The other thing with operator protection in particular is insulation coordination, environmental values, and so I've indicated the default values we use over voltage category 2, pollution degree 2, material group 3B, and altitude 2000. So those generally suit us for customer needs. With the patient tables, they've already taken into account those values, maybe more severe values, since the values are stronger, more severe, stringent. Patient tables don't have the need for you to kind of use your assumptions. They're built in. And 3,000 meter altitude is built in as well. So if we go back to our insulation diagram and use those tables, we can look up 2 means for 5 patient and 1 means for mains. And in fact, the 5 is about a 3.4 creepage, and the 1 means for mains is 4. So we'd use the 4. The 2 means for 5 is around, I think, 1.6. And the 1 means for mains is 2.5. So we're going to use the 2.5. And the 2 MOPP for 5 volts would be about 1,000 volt dielectric. And the 1 means for mains is 1,500. So again, that one's higher. We'd use the 1,500 for verification. Remember, A has the potting material, so there's no creepage and clearance, assuming we can pass our thermal cycling. And the dielectric could be 160% of that 1,500, so that's 2,400. C is our operator area for 5 volts, and if we look that up, it's 1 millimeter creepage for 2 means and 0.8 millimeters clearance. And the dielectric strength, because we want to protect a patient contacting those voltages, so we do want to have an insulation strength, would be 800 volts. Now, if it was really only operator contact, we wouldn't really need any insulation. We'd actually allow contact, right? But if the patient's around, well, that could be exposed. That's no good. So we're going to show that we have some separation there. All right, so if we know our insulation values, we can go ahead and build something. Lovely. And we presumably want to do a lot of functional things and mechanical things, and et cetera, on the verification side. But we're talking about electrical protection, so our test plan would kind of follow from that insulation diagram. We have an area A where a thermal cycling test needs to be done with 160% dielectric. We have an area B and C where we have some plastics. So we're going to check creepage and clearance. B is the pseudo applied part F, and the area C is the, did I say B before? B is the pseudo F. C is that operator display button. So there's the applicable creepage and clearance for those two areas. Areas A and B, A is the applied part, B is the pseudo F type. We would do patient leakage as well as a mains on the applied part patient leakage. And that needs to be done before and after a 7-day humidity conditioning test. It's 93% humidity. The home care collateral requires an IP22 because it's transit operable. It moves while it could be moving while it is providing its intended use, its clinical function. So anything more than IPX0 needs 7 days for humidity. Area C was our operator area. For leakage, we'll do touch current. And again, before and after our 7-day humidity. And then last, areas B and C, which were our plastics, our pseudo F type, and then our operator area. We're going to do dielectric strength, the appropriate dielectric strength for each area, again, before and after 7-day humidity. So, let's hope we pass after we've built this wonderful thermometer. And that would then demonstrate we've got a safe thermometer. Nobody's going to get shocked and related. All right, so for review, categorize your touch surfaces, classify the applied part, risk assess your accessible parts, MOOP, put your insulation diagram together, look up your insulation parameters, and then your test program follows from that. Okay, and that's hopefully helpful. If you liked it, let me know. Maybe I should do another one. Our website has free resources. We've got a bunch of help files we've written up on frequently asked questions we get about various things. What's essential performance? When can I use a non-medical power supply for my medical product? All these wonderful kind of issues that come up a lot. We also offer training workshops. We have one scheduled in October in Boston. That's October 2020. All right. Thanks for listening. And, I hope it helped. Thanks.